In the previous presentation, you saw that Q was equal to the sum of degeneracies G sub I, e to the minus epsilon, the energy of a particle, over kT, in what is an example of a partition function, where a partition function is also called the sum over all states. N sub I, the number of particles in any given state, is equal to the degeneracy of that state, G sub I, e to the alpha minus epsilon over kT, where alpha has not been solved for yet. However, a simple substitution where one can trivially say that the total number of states is equal to the sum of each individual state, you get e to the alpha on the outside of the sum times the sum of the degeneracies, e to the minus alpha over kT. Therefore, if one divides, the alpha simply cancels, and n sub I over n is equal to the population of a single state, G sub I e to the minus epsilon sub I over kT, over the sum of all states, G sub I e to the minus epsilon I over kT. This is equal to something called the Boltzmann Distribution, which is essential to statistical mechanics. Using the Boltzmann distribution, one essentially finds the population of any given energy level. For example, you were told that at room temperature, most vibrational states are in the V equals 0. How true is this? In other words, what percentage of HCl molecules are in the V equals 2 state at 25 degrees C? In this case, vibrations are all singly degenerate, so G sub I equals 1 for all levels. The energy of each individual state is equal to V plus 1/2 h nu, where for HCl, the vibrational frequency nu is 8.66 times 10 to the 13th hertz. So, rather lengthy, but still straightforward. If we're looking for state number 2, your numerator is e to the minus 2 plus 1/2 h nu over kT, where T is 298 degrees Kelvin, times the sum of e to the V equals 1 plus 1/2 h nu over kT, e to the minus 1 plus 1/2 h nu over kT, and so on, up to e to the minus 4th plus 1/2 h nu over kT. This theoretically should go on forever. However, when one does the arithmetic, one finds the population of the V equals 2 state is 7.1 times 10 to the minus 16th. The V equals 0 state is much larger at 9.3 times 10 to the minus 4th. And going further than V equals 4 is rather pointless because we are already at a population to 10 to the minus 28th. The population numbers themselves are rather obscure. The Boltzmann distribution simply gives the ratios. So when one does all of the additions, one finds the population of the V equals 2 state, 7.1 times 10 to the minus 16th, divided by the sum of all the other states, simply winds up being equal to the sum of V equals 0, 9 times 10 to the minus 4th. A very small number is then obtained, 7.6 times 10 to the minus 13th. What these numbers mean is that at 25 degrees C, 7 times 10 to the minus 11th percent of all molecules in a room will be in the V equals 2 state. Essentially, 100% of the molecules will be in the V equals 0 state, as had been previously stated. Now we use all these statistics in what is called statistical thermodynamics or statistical mechanics, where we use quantum mechanics to determine Q, the partition function, for a single molecule. As you know, energy is equipartitioned between translational, vibrational, rotational, and electronic energy. through the particle in the box, the translational energy has been measured at epsilon is equal to n squared h squared over 8 ml squared. Applying the math for the partition function, we find that the translational partition function is 2 pi mkt, where the m is the mass of one particle in kilograms to the 3/2 divided by h cubed. We have also already solved the vibrational energy at v plus a half h nu. The vibrational partition function, again by solving the differential previously shown, is 1 over 1 minus e to the minus h nu over kt. Rotational energy for a rigid rotor is j times j plus 1 times the rotational constant h over 8 pi squared times the moment of inertia times the speed of light. There are two possibilities here. If one continues with a rigid rotor, in other words a linear molecule, the rotational partition function is 2 times the moment of inertia, kt, over something called sigma h cubed. However, for a nonlinear molecule, where you can have a moment of inertia in the x, y, and z direction, the partition function is 8 pi cubed times the moment of inertia in direction a times the inertia in b times the inertia in c to the 1/2 divided by kt to the 3/2, and that divided by sigma over h cubed. Sigma is known as a symmetry number. It is intrinsic to a molecule. For example, a linear diatomic like nitrogen would have a sigma of 1. It doesn't matter how you turn it. HCl, on the other hand, is linear, but it has two possible directions, so sigma is 2. The electronic energy, the energy of each individual state, is actually measured spectroscopically. The partition function for this is the degeneracy of the ground state plus the sum of the degeneracy of each individual state, e to the minus epsilon sub I over kt, where again, epsilon sub I would be the recorded energy of each individual orbital, the 1s orbital, the 2s, the 2p, and so on. Therefore, if we wish to record a thermodynamic property, the following would apply. For example, if we want to look at delta U, the total internal energy, the first property examined in pchem 1, first, you have the equipartition of energy, which means for the conditions given, one must calculate the change in the translational energy, which is equal to the change in the log of omega translational divided by the sum of the change of all the logs of all of the sigma translationals over the change in n times the sum of all the translational energy. Similarly, the same differential has to be set to 0 to find the max, the most probable state, for the vibrational energy, the rotational energy, and the electronic energy. After these derivatives are taken and solved for the maximum, you simply then just add up the translational internal energy, the vibrational internal energy, the rotational internal energy, and the electronic internal energy to get the total delta U. It's that simple. Obviously, this is not simple. Fortunately, all of the energies, translational, vibrational, rotational, electronic, are known. Therefore, all of the partition functions and omegas, translational, vibrational, rotational, electronics, and their derivatives are already calculated. In other words, somebody who is really good at math did all the work for you already. The results of these calculations are seen in the following tables. Already solved. Delta U, the molar internal energy, has a translational contribution of 3/2 RT per mole, a vibrational contribution of sigma theta V, where theta will be explained later, E over E to the theta V over T minus 1, a rotational contribution to the delta U is R times T per mole, and electronic transitions contribute nothing to the total internal energy of the molecule because those transitions are internal. For the enthalpy, the translational portion of the enthalpy contributes 5/2 RT. The vibrational portion contributes the identical sum of theta sub V over E to the theta sub V over T minus 1. The rotational part of the delta H is again RT, and the electronic contribution is again 0. For the molar entropy, things get longer. Translational contribution to entropy is R times the log of 2 pi mkt over h squared to the 3/2 times kt over p, and that entire log is plus 5/2. The vibrational contribution is minus R log 1 minus e to the theta v over t. Now you have a rotational contribution of R log T over theta R, sigma, plus 1. And there is an electronic contribution of R times the log of the degeneracy of the ground state. For the Helmholtz energy, the molar energy delta A, you have a translational contribution of RT log 2 pi mkt over h squared to the 3/2 kt over p plus 1. A vibrational contribution of the sum of all of the RT log e to the 1 minus theta v over t's, rotation minus RT log t over theta r sigma, electronic minus RT log of the degeneracy of the ground state. For the molar Gibbs free energy, similar outcomes. The translational energy is identical without the plus 1 at the end, RT log 2 pi mkt over h squared 3/2 kt over p. The vibrational contribution is the identical RT log 1 minus e to the theta v over t. And the rotation is once again minus RT times the log of t over theta r sigma. And the electronic contribution is also identical, RT times the log of the degeneracy of the ground state. While these are long, they are actually fairly simple plugging in numbers. M in all cases is the molar mass in kilograms per mole in order to get joules. As always, the temperature is in Kelvin, and the pressure is in pascals. The sigma in the rotational energies is the symmetry number. As mentioned before, these are intrinsic to molecules and will be given. G0 is the degeneracy of the ground state as stated. This is also intrinsic and given, or you can determine it yourself through the term symbol of the ground state. It is essentially the spin multiplicity. Theta is what's called a Debye temperature. It is calculated as H times eta over K, where eta is a general form of any type of frequency. For theta R, the rotational Debye temperature, theta is omega, the annual frequency, or how many degrees theta per second, the rotation times the rotational velocity. This is a given for a given molecule. This will be known. For the vibrational Debye temperature, theta V, eta is equal to the fundamental vibrational frequency of that molecule, nu 0, which is also a given. So essentially, the Debye temperature simplifies things by throwing in a couple of constants, h and k, into one case. And it also represents, in all cases, theta over t, what percentage of the maximum energy a molecule happens to be at. Once again, the point of statistical mechanics was to relate quantum mechanics to what you've already learned in thermodynamics. So filling in this table a second time. In classical thermodynamics, you learned that an ideal monatomic gas has a delta U of 3/2 RT, while an ideal multiatomic gas is 5/2 RT. Looking at the statistical mechanics, the translational energy contributes 3/2 RT for a multi-atom molecule, while the rotational energy contributes an additional RT, giving you the 5/2 RT for the ideal case. Non-ideality comes into play through the vibrational energy of the molecule, which is small but still present. Similarly, for the enthalpy, you learned in classical thermodynamics that an ideal monatomic gas has a standard enthalpy of 5/2 RT, while a multi-atom molecule has an ideal enthalpy of 7/2 RT. This is again taken up in statistical mechanics, where for delta H, your translational energy contributes 5/2 RT. Your rotational energy once again contributes RT to give the 7/2 of the ideal state. And once again, the vibrational energy is what introduces the non-ideality and gives you the actual value of delta H. We'll skip entropy because it is the same holds true, but it's complicated and hard to fit on one slide. So we will now move to delta A, where you learned that delta A is minus SDT plus minus PDV, the work of the molecule, the work of the system. If you'll remember, under certain conditions, minus PDV is equal to minus RT log V2 over V1 when I have a constant pressure. If you look at the translational energy, you have minus RT log of 2 pi mkt over h squared to the 3/2 kt plus p. Referring to the entropy, you will note that this is essentially the entropy times T with the negative sign in front, or minus SDT. Similar in form, RT log V2 over V1, you now have minus RT log T over theta R sigma. And in this case, non-ideality is contributed to by both vibrational and electronic energies to the total Helmholtz energy of the molecule. Similarly, under a constant temperature, delta G is minus SDT minus RT log V2 over V1 again. For, an adiabatic system, where once again, that is your ideal outcome. Your translational energy is again RT log 2 pi mkt over h squared to the 3/2 kt over p is equal to minus SDT, because it's equal to essentially the delta S per mole from the table times a negative T. The rotational contribution essentially donates the minus RT log V2 over V1 as minus RT log T over theta R sigma. And once again, the vibrational and electronic energies give non-ideality. So, at the end of the day, statistical mechanics does two things. It allows quantum mechanics to merge with thermodynamics, because the universe can only operate under one set of laws, whether on the small scale or the large scale. But additionally, as can be seen here, it quantifies reality. It adds the non-ideality to the thermodynamic functions to give a more accurate outcome in predicting the thermodynamic properties of any given molecule.